In this video series, I want to introduce you to complex numbers and some applications in physics and engineering. First of all, I want to talk about the motivation for the introduction of complex numbers. This was mainly done by a historical mathematical problem. The mathematician Gerolamo Cardano in 1545 put forward the following problem. Find two numbers of which the product equals 40 and the sum equals 10. For this problem, we just find the two conjuncted equations. The first one, if we call the first number x1 and the second number x2, x1 times x2 equals 40, and the second equation, x1 plus x2 equals 10. Now if we solve equation 2 for x1 and insert into equation 1, we get the expression or the equation x2 times in brackets 10 minus x2 equals 40. And now we can multiply the brackets and we get to this equation. And now we remember the fact from the calculation with real numbers that a real quadratic equation gives two solutions, x1 and x2. Therefore, we consider x1 and x2 as the results of the following quadratic equation. X squared minus 10x plus 40 equals 0. We can construct different problems for which this always gives an answer within the real numbers. For example, that the product equals 30 and the sum equals 10. But what happens here? The general solution for this equation within the real numbers is the so-called midnight formula. If you have a quadratic equation in standard form, x squared plus px plus q equals 0, then the solution gives two numbers, x1, 2, equals minus p over 2 plus minus the square root of p squared over 4 minus q. And in our problem, if we compare it with our standard form for the quadratic equation, we immediately see that p equals minus 10 and q equals 40. And if we use the solution formula, we get the following answer. x1 equals, you can see, minus pi over 2 is 5 plus the expression under the square root. And this gives minus 15. So we have as an answer x1 equals 5 plus the square root of minus 15. Now within the real numbers we would cancel, we would give up and say that there is no solution for this problem. But we can continue. We can, first of all, we can separate the expression under the square root. We can divide it into two parts. We can say that each negative number is minus 1 times the number itself. So minus 15 equals minus 1 times 15. And then we can separate it in two square roots. And we have the answer x1 equals 5 plus the square root of minus 1 times the square root of 15. And now the square root of 15 is well defined. This gives 3.87. And what's left is the square root of minus 1. And for the second solution, we get 5 minus the expression under the square root, and this is in this case 5 minus the square root of minus 1 times 3.87. But yeah, as you can see, we did not really solve the problem because we still don't know what is the solution of the square root of minus 1. So the problem was that there were no rules for square root of minus 1. We would need a number of which the square gives minus 1. So how to continue? We could just define a number I with following property, that I squared equals -1, so that I equals the square root of -1. And then our result just would read for x1 equals 5 plus I times 3.87. We just exchange the square root of -1 by this I number, which is called the imaginary unit. And for the second solution we would get 5 minus I times 3.87. But first of all, mathematics has to define rules of how to handle this I number in connection with the real numbers, how to build meaningful operations like addition or multiplication. In the first time after introduction of this I number, which is called imaginary unit nowadays, this was just considered to be mathematical conjuring. But it turned out that these numbers can complement the real numbers in a way that leads to meaningful mathematics. It was mainly the work of Augustin Louis Cauchy and Carl Friedrich Gauss and William Rowan Hamilton in the 19th century which led to great breakthroughs in the development of complex number theory and application. Now we continue with the second part, or the second big topic, definition and basic calculus with complex numbers. Now, without disturbing you with the exact mathematical definition, we take a practical road. The following equation leads directly to the I number, the imaginary unit. X squared plus 1 equals 0. So, and now we know how to solve this equation. We have two solutions. X12 equals plus minus the square root of -1, and this is plus minus the square root of I, and therefore I squared equals -1. With this imaginary units, complex numbers can be constructed as follows. And as example, see the solution above. We can define a complex number set written as a set and a line above it. A set is defined as a real number A plus the imaginary unit times a real number B, where A and B are any real numbers. They can also be 0, but if B equals 0, then Z is not a complex number, but Z is just A, and A is a real number. And I equals the square root of -1. We call this the Cartesian form of complex numbers. Okay, now let's go to the addition and subtraction of complex numbers. And you will see that this is really easy. If we want to add two complex numbers, Z1 plus Z2, then we can calculate it by separately add the imaginary part of the numbers and the real parts. This means if I have the first complex number, Z1 equals A plus I times B, plus the second one equals C plus ID, then first of all I add the real parts of the two complex numbers, A plus C, and then I separately add the imaginary part. This means plus I times B plus D. So I treat this I number like a variable x, and separate it from the addition of just only the real numbers. And you can see this example here. If I have the number 1 plus I times 2 plus another complex number 3 plus I times 4, I will add the real parts, 1 plus 3 gives 4, and I add the imaginary parts, 2 plus 4 gives I times 6. Now let's continue with multiplication. If I want to multiply two complex numbers, Z1 times Z2, this is defined as almost like in real numbers, like you would multiply two brackets. First of all, we will multiply the brackets. It would mean I times C. A times C. Then we can multiply IB times ID. And this is where this minus comes from, because plus I times plus I is I squared, and I squared is minus 1. Minus 1 times B times D equals minus BD. And then we get the other factors, IB times C and A times ID. So we bring I out of the brackets and have just ID plus BC. And here you can see the example.